Hello, I apologize. The last video got muted about halfway through, so I'm going to re-record that part. You'll be able to hear my voice this time, I hope. The last video you're able to still watch. I just don't think you were able to hear anything I was saying. So here we go, take two. I think we left off right about here. We were just finishing our thoughts on the rows and talked about how that inside coefficient n, if it was even, you double n to get the number of petals, and if n is odd, that number n represents how many petals there are. And I just wanted to leave you with the thought while you're doing your homework to maybe think about why that is, like why do we double n if it's even, and why don't we double it if it's odd? And so I'm going to just kind of leave that hanging and let you think about that while you're doing your homework and see if anything strikes you. And if not, I'll be happy to discuss it in the next video, or you can email me to ask questions about it, or offer ideas. But I think it might reveal itself to you. If not in this lesson, I think maybe in our next assignment there might be a problem that we do where it might help us understand why that is. So just something to think about. And I wanted to do our one other example, and since I've done it once already, I actually saved my notes, so most of this is filled out already, and so maybe that'll help us go through things a little bit quicker. So this equation is r squared equals 4 sine times the quantity 2 theta. And as always, we like to check for symmetry, and just wanted to offer another reminder that I really want you to do that in your homework again. I know that's probably starting to feel kind of redundant, but please, one more time, if you could do that for me. You'll notice this equation is a little different because it's r squared, and so that's going to leave us with a few things to talk about. But let's just go ahead and check for symmetry first. So replace theta with negative theta, and since sine is odd, this ends up being negative 4 sine 2 theta, which is different. So it will not be symmetric over the polar axis. If we replace theta with pi minus theta and use the identity for the sign of a difference, we end up with negative 4 sine 2 theta, and that one is also not symmetric. This time, though, you'll see how or why replacing r with negative r could actually work, and it's because we're squaring r. So when you square negative r, you get r squared, and you're back to the original equation, and so this one will be symmetric over the pole. And so we'll want to keep that in mind as we're making our graph. So here are some points that I've already laid out for us that I think will work. I'll talk you through them, though. I know it's a lot to look at all at once. And so start with an easy value like 0. 2 times 0 is 0. Sine of 0 is 0. And 0 times 4 is 0. Also keep in mind that for this one, since it's r squared, whatever value you get after doing this computation, you want to take the square root of that. So that doesn't change anything for 0 because square root of 0 is 0. Anyways, we can go to our graph and start with 0 as our point right at the pole. If you try something simple like pi over 2, 2 times pi over 2 is pi, and sine of pi is also 0, so you get 0 again. If you try something like pi, same thing happens, you get 2 pi. Sine of 2 pi is also 0. In fact, any multiple of pi over 2 is going to give you an r value of 0. So 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on. Those values are going to continue to give you 0. So the next value I went to was pi over 4, and normally I avoid pi over 4 because it has a sine or cosine value of root 2 over 2. But in this case, since we're doubling the angle first, pi over 4 becomes a great choice, because when you double pi over 4, you get pi over 2. And sine of pi over 2 is 1, which is a nice number. 1 times 4 is 4. But you'll notice down here I don't have a 4 in the place. Again, the reason why is because it's r squared equals 4. So take the square root of that, and you get plus or minus 2. And so let's see what that looks like on the graph. I'm going to go to pi over 4, 2, so I'll go out 2 units. But since I do the square root, it's plus or minus, so I can go backwards 2 units as well. And that's going to be along the line pi over 4, or sorry, 5 pi over 4. Which is interesting because that's the next value I might have chosen. 5 pi over 4 would also give me a nice value when I double it. You get 10 pi over 4, which is the same as 5 pi over 2. Sorry, 5, let me take that back. So when you double 5 pi over 4, you get, no, I said that right the first time. So you get 10 pi over 4, which is 5 pi over 2. And so the sine of 5 pi over 2 is, that angle's in the same location as pi over 2, so that's 1 again. 4 times 1 is still 4, square root of 4 is still plus or minus 2. So you'll notice that doesn't add anything to our picture, though, because if I go to 5 pi over 4 and go out 2 units, that is the same place that I put the point just a moment ago. And if I go negative 2 on that one, it's still the same point that I already have. So that doesn't change a whole lot. Also, if we use our symmetry here, I guess that doesn't add anything either, because symmetry over the pole is kind of like being symmetric over the origin. And you might remember when we use symmetry over the origin, that's kind of like flipping it over the x-axis and the y-axis alike. So if I were to flip it over the x-axis or the polar axis, that puts us down here at 7 pi over 4. And then if I flip it over pi over 2, the line pi over 2, that puts me over here. So I guess I could have used symmetry when I did the first point, but since I had the plus or minus 2, it was really easy to go ahead and find that point anyways. And so at this point, symmetry is not really helping us. Okay, so then some other points I tried. This might be the first time I've used pi over 12 or a multiple of pi over 12. Normally, I would avoid those, but remember, we're doubling the angle first before we find the sine. So I like the sine of pi over 6 is a great choice because the sine of pi over 6 is a half. And so I thought to myself, well, to get pi over 6, I need to know what number do I double to get pi over 6, and that number is pi over 12. So that's why I picked pi over 12. If you double that, you get the pi over 6 that I just mentioned. Sine of that is a half. And then 4 times a half is 2. Take the square root of that, you get plus or minus root 2. And so then if I go over here, so pi over 12 and root 2 is about 1.4 is the value there. And so I'm going to go just under 1.5 units. So I'll go out to about right here. And then let's go ahead and use symmetry to help me out. So again, if it's symmetric over the pole or the origin, I'm going to flip it over the polar axis first. So that would just take me about here. And then if you flip it again over the y-axis or the line pi over 2, that takes me over here. So that'd be 13 pi over 12. And you'll notice I went ahead and wrote that value on my table. The next nice value on the unit circle would be for sine, like 5 pi over 6 would be a great choice because it also has a sine of 1/2. But we don't want to pick 5 pi over 6 because we have to double it first. So I took half of that number, 5 pi over 12. And then when I doubled that, that gave me the 5 pi over 6. It has a sine of 1/2. 1/2 of 4 is 2, so I get the same value, square root plus or minus square root of 2, which again is still 1.4 approximately. And so this time I'm going to go to 5 pi over 12, so that would be right here, and go out the same distance, about 1.4. And then if I use symmetry again, how about let's flip over the y-axis this time. So it's going to take me to 7 pi over 12, and then flip over the x-axis. That takes me to 17 pi over 12. So down here, right about here-ish. And that's why I have 17 pi over 12 on my chart as well. All right, so at this point, I think I see what's going on. It looks like I'm going to follow this pattern this way. And we end up with a graph that looks kind of like this. And your first thought might be that, hey, we've got another rose with 2 petals. But you'll notice the format of the equation is a little different than our rose format. So if I go back to our rose format, I would think a rose with 2 petals would have an n value of 1. So it would just be A cosine theta or a sine theta. And also notice it's just r equals instead of r squared. And so when I look at this one, it's r squared. And also notice there's a 2 there, not a 1. And so this is a little bit different format. I suppose if it wasn't r squared, this would be some sort of rows, but since it's r squared, it gives just a similar looking picture. It looks like something with petals, but the terminology that mathematicians have given this figure is the lemniscate. And so that's another new one to us, of course. And so you might be wondering, well, how do I recognize a lemniscate versus the rows? Well, by just looking at the graph alone, it might be a little challenging to do that at times. But I can say that a lemniscate only ever has two petals. It won't ever have more than that. Also, you can recognize it, of course, from the equation because it has r squared rather than r. And so anytime it takes this format here, it's going to be a lemniscate. And so as we did for the previous example, I have a few more equations for you, maybe to try on your graphing calculator if you've been playing along at home. So we just graphed this one here, the r squared equals 4 sine 2 theta. So I might encourage you to try a 9 here and see how that changes your graph. And then maybe leave the 9 and then put a cosine in there and see how that might change your graph. So I would encourage you to maybe pause the video again and play around on your graphing calculator and see what happens. Okay, so if you're back with me now, let's see if we agree. So here's the graph that matches pretty close to what I drew by hand. I'm noticing this kind of hugs the x-axis a little bit longer than maybe my graph did. So perhaps if we, fine-tuned and put some extra points in there, like smaller points, like pi over 24 or something like that, perhaps we would have seen that a little more clearly. But I'm pretty happy with our picture here. It certainly looks close. And then probably what you expected to happen when we put that 9 in there, it just kind of lengthens how far out that petal goes. And you'll notice the petal doesn't go out 9 units, but instead it goes out the square root of that number. And so, if this is a 9 here, the square root of 9 is 3, and so this distance ends up being 3 units. Or over here on this one, since that's a 4, this distance ends up being 4 units. And that's a little bit different than the rows where the coefficient here is the actual length. So it's not the square root of that number, it's that number. And so that is a difference between the rows and a lemniscate that you may want to note of. And so just keep that in mind, whatever this coefficient is, the square root of that will be the length. And then for the last one, when we change to cosine, a cosine is still a lemniscate. The only difference is just the orientation. It does that rotation, kind of like the rows did. So it looks like it's rotating 45 degrees, just like the rows. And I think the reason that is because the 2 here. And so normally the difference between a sine and a cosine would be 90 degrees. But since that 2 is there, that compression and that shrinks that rotation from 90 degrees to 45. And so with that rotation, you can kind of see the petals are kind of hovering above and below the x-axis, whereas with the sine, those are more in between the axis in those open spaces in quadrants 1 and 3. One bit of advice: if you tried graphing these and they don't look exactly like mine and they have a little bit of open space, like see down here where the blue is, yours may have had like a gap here. Actually, 2 things I should mention. Maybe I should back up and speak one other thing before I get to the gap part. I apologize, I got a little bit ahead of myself. You might be thinking, well, how do I even plug in r squared to my graphing calculator? I should have given you a little heads up before I let you loose on how to do that. So I don't know, maybe you came up with something. How did you do that? Well, let's take a look. So the issue is on our calculator, we just have r equals. We don't have a choice for r squared equals. So we're forced to tell it what r equals, not what r squared. Well, if we know what r squared is, we can certainly find r, can't we? just take the square root. Now the problem is those equations, while very, very similar, they're not exactly the same. If I simply just type in the square root of, I think I have the third one in on my calculator here, so this one down here, if I type in the square root of 9 cosine 2 theta, and I graph this, you'll notice in this little window down here, do you see how there's this little gap, and it's not graphing the entire thing? And the reason why is this equation here doesn't fully represent this equation that we have right here. It's very similar, but it's not exactly the same. So what we have to do is when we square root an equation, don't we have to do plus or minus? And so that's what we're going to have to tell our calculator. Okay, so we're going to do R1 equals positive square root of 9 cosine 2 theta. And then for R2, you have to do the opposite. So negative square root of 9 cosine 2 theta. And so then if you graph that, that should give you the complete picture. And so let's see what happens here. So do you see how the blue, I think, is my R1 and the red is my R2, and when you put those together, you get the complete graph. If you only have R1 or you only have R2, I think you're going to, again, have that gap perhaps show itself. Now, if you've done both of those things and your graph still is not complete, there's one other thing you might need to do, and that's what I was about to tell you a moment ago. And previously, when we changed our window values when graphing, I encouraged you to put 2 pi for theta max. And remember, theta max, that's theta is our input, and so usually we have like an x max. And you might remember having these same frustrations when we were graphing way back in chapter 1 and chapter 2, is if you didn't make your input window large enough, you didn't get to see the entire graph. You may have only seen part of the graph. Well, now theta is our input, and to see the entire graph, we have to make sure that window is large enough. Well, for most of the other graphs, 2 pi has been a perfectly fine window. But let's look back at our equation that we're trying to graph here. Notice there's a 2 on the inside. And since there's a 2 on the inside, remember we're compressing our graph. And so if our window 0 to 2 pi used to be adequate, with a compression, now we need to double that window for the entire graph to reveal itself. Does that make sense? So instead of a window of 0 to 2 pi, now we need to have a window of 0 to 4 pi. Because it's going to, our period, remember that term period? The period is how long it takes for the graph to complete its cycle. And so our period is no longer 2 pi, it's now 4 pi. And so if on your graphing calculator you have theta max of 2 pi, it's not going to reveal the entire graph. It's only going to show part of it. And so that's something that you can do. Now that doesn't mean 4 pi needs to be your theta max on every graph that you ever do, but I would suggest that anytime there's a 2 in here, you might want to change that. Or if there's another number like 3, 4, or 5, then you might need to increase that even more. Okay, so to summarize our lemniscate, it's going to take the form of r squared equals a squared cosine 2 theta, or r squared equals a squared sine 2 theta. Just a few highlights here. Obviously, r is no longer r, it's r squared, but also that front coefficient is no longer a, it's a squared. And so if you're curious as to the length of the pedal of the lemniscate, you want to make sure to take the square root of that. So I guess technically a is still the length. It's just that number in front is no longer a, it's a squared. And so if you're needing to know the length of that, make sure you take the square root of that value. And then the lemniscate can either have a cosine or a sine value. If it's a sine, remember it's going to look like one of these two graphs on top here. And if it's a cosine, it's going to be more hovering just above and below the polar axis or the x-axis. All right, so that kind of wraps us up for take 2 of our video. Your homework is here. There's only 6 problems, so take your time, work your way through them. again, I'd really like you to go through these steps here. I'd like you to check for symmetry. I'd like you to show your input-output table, and then obviously your graph is your final answer. But I think these two steps are important. I realize that once we have formulas like this and we start to recognize what these things are before we graph them, you might start to feel like you don't need to do these things. But I think just like with the last two assignments, we're still in the exploring phase, and some of these graphs are brand new to us. And so I think the more exploring you do, the more you'll take away from this assignment. And so I'm going to ask that you continue to do this. And if you are starting to notice those patterns and recognizing things before you graph them, that's awesome. That's a great place to be. And that's certainly where we want to end as we wrap this unit up soon. But again, if you could just kind of show me that you've gone through this process, that would be great. So thank you for tuning in. If you have any questions, please reach out as always and let me know how I can help. Good luck.